As an avid crypto, Ethereum, and DeFi user and enthusiast who has been following the community and development for almost 4 years now, it's a huge honor to be invited to participate in this conference. My name is Leart Ulaj, and I'm a product manager at Avalanche. I've been at the project for a few months after spending almost 2 years at Gemini in their market surveillance team. Since joining, I've been working with our team to try to find ways to showcase the functionality of our system to existing cryptocurrency users and create avenues that make it accessible to them in a way that they are already familiar with. So, because Ethereum is the focal point of innovation and collaboration in the crypto world, one of our largest efforts in this regard has been the deployment of a bridge between the Ethereum chain and one of multiple chains on our network. We believe this will encourage experimentation and further connect the cryptocurrency ecosystem, thereby growing the cumulative share of use cases and developers that are in the ecosystem. So we firmly believe that interoperability and collaboration will benefit all of the networks that are involved. So before I start discussing the implementation for the bridge that we chose and getting into specific details, economic considerations, and use cases, I'd like to start by first giving a brief overview of the Avalanche platform. Broken down into the three most notable features, the Avalanche platform comes down to its novel consensus algorithm, which allows for unmatched performance. The platform has interconnected networks, enabling compounded network effects as a topology forms, and the ability to launch any virtual machine to a secure chain, massively reducing friction for avid users who are coming from any corner of the cryptosphere. So first, unlike Bitcoin and Ethereum 1.0, which operate on Nakamoto consensus, or other multi-chain projects that are using variants of classical consensus protocols, our platform is built on a novel consensus algorithm, which utilizes gossip mechanisms and metastability to reduce message complexity. Okay, so what that really means for Avalanche is that it can scale to a high level of network activity while also scaling in the number of participants. Specifically, the number of consensus messages that a node sends to process a vertex in the instance of a directed acyclic graph or DAG, or a block in the instance of a chain, is constant relative to the validator set size. So a node needs to send the same amount of messages regardless of how many validators are active. So our consensus protocol also features 1 to 2 second transaction finality and quiescence, which means that when the network is not having transactions sent through it, it won't produce blocks. Secondly, we have been able to build a network of networks. So what that means is, unlike the previous paradigm where you had a single chain and a single validator set associated with that chain, Avalanche enables a heterogeneous network of blockchains and subnetworks, which on our platform are dynamic validator sets that can validate one or multiple chains. So validators in our model can manage their own membership, choosing to participate and allocate resources to the subnets that are relevant to them, with the only exception being that all validators must validate the primary subnetwork. Our subnetworks can also be designed to be permissioned or permissionless, which allows for a greater variety of financial applications to be developed on top of them. What this means practically is that as a node, I might come along and join Avalanche's network. And hypothetically, if I'm a bank or some other kind of institutional user, I might choose to participate in a permission subnetwork that's related to traditional financial instruments. Alternately, if I'm a crypto enthusiast like myself, I may choose to join a permissionless subnetwork that contains chains with VMs compatible with a popular project like Bitcoin or Zcash or any other project of choice. So this brings us to our final main feature. Avalanche allows for each chain on the network to operate with its own virtual machine. This can be an implementation of an existing VM or something new entirely, as we've mentioned. Layering existing virtual machines on top of Avalanche makes the interaction with our platform for new users and developers considerably easier. It reduces friction that is related to tooling, network, consensus, and state. Some examples of VMs are in Avalanche's default subnet. Considering we are at ETHCON, I would imagine that EVM will be the most familiar to this crowd. So our primary network consists of 3 built-in blockchains. Our primary asset minting and transfer chain, the X chain, is actually a directed acyclic graph, or DAG, with vertices rather than a chain with blocks. In this environment, users can mint fixed and variable cap assets along with NFTs and transfer tokens at throughputs that are orders of magnitude higher than existing solutions. So our P and C chains both use the Snowman consensus protocol, which is a chain optimized version of Avalanche consensus, allowing essentially the execution environments to work in a chain structure rather than a DAG structure. So the P chain manages validation, delegation, along with subnets and chains. So the X and the P chains are both examples of new VMs, and the main subject of discussion today is the contract chain, or the C chain, which is an implementation that is fully compatible with the EVM. So considering that it's fully compatible with the EVM, it is obviously the target for interoperability with Ethereum. So developers will be able to use the same Solidity contracts and the same tools that they currently use on Ethereum. Fortunately, the team at ChainSafe has built Chain Bridge, a multi-chain Solidity and substrate compatible trusted solution. Okay, so ChainBridge uses Solidity smart contracts to enable transfers to and from EVM compatible chains. To balance the goals of extensibility and compatibility with existing standards, ChainBridge directly supports 3 types of transfers: fungible, non-fungible, and generic. There are handler contracts for each of these types, along with a core bridge contract and a safe contract. The bridge contract is responsible for initiating, voting on, and executing proposed transfers, and the handlers are used by the bridge contract to interact with other existing contracts. All transfers take the same path, and I'll describe it, and we can take a deeper look at this diagram, but I'd like to first define some basic terminology. So a relayer is an instance of the bridge software. Relayers are the intermediaries between chains. They're listening for events on the relevant contracts to route to destination chains. A proposal is a transfer request from one chain to another, and the proposal is created by a relayer. It must then be voted on by other relayers until it meets the relayer threshold, which is the number of required votes to pass the proposal. The chain ID is relatively self-explanatory. It's simply a unique identifier for a single chain. Because ChainBridge is a multi-chain solution and connect to an arbitrary number of chains, this means that in the future, our deployment could potentially be connected to other functional EVM chains, whether they be on other projects or on subnetworks within the Avalanche platform itself. And finally, the resource ID is a unique identifier for an on-chain interaction. For instance, a resource ID would be associated with a specific ERC20 token, say wrapped Ether, and would denote the contract addresses of the asset on each chain, along with the origin chain of the asset, which would in this case be Ethereum. Okay, so with all of this information in mind, let's walk through what a transfer flow actually looks like. So in this ERC20 example, we start with a user, Alice, on blockchain A, who initiates a deposit to the bridge contract. So this action is then dispatched to the ERC20 handler contract, and because the token originates on blockchain A, the asset is locked in a safe contract, and a deposit event is emitted. That event is then read and passed on by the relayers. In this scenario, relayer 1 is the first to process the deposit event, and they create the deposit proposal on blockchain B. Relayers 2 and 3 will subsequently vote on this proposal until the relayer threshold is met. Once that happens, the bridge contract will execute the deposit and call to the handler contracts in order to adjust the corresponding ERC20 token balances on blockchain B to the address specified. In this instance, Alice is transferring the tokens to herself, but the receiving address can be any address that the initiating sender desires. Okay, so as far as the set of relayers on the bridge, this set must actually be registered and maintained by a administrator. So the setup of this bridge is in fact trusted. The administrator of the contract has the ability to alter the relayer threshold, add and remove the relayers who are listening for and creating proposals, register resource IDs, and set and update the bridge fee. The bridge fee is paid in the native token of the initiating chain of a given transfer event and is denominated in way. So if I'm sending from Ethereum to Avalanche, I would pay the bridge fee in some amount of Ether. Okay, so in an attempt to mitigate the centralization point of administration, our partners who will be participating as relayers will set the administrator of the bridge to be a gnosis safe, controlled by the collective group. By adding this to the bridge setup, there's a greater assurance that the relayers will not be hijacked or behave adversarially. This course of action was taken as a result of our and our partners' desires to build what we believe to be a functional and a legitimate solution. Coordination across multiple organizations across the world can be challenging and is an ingrained part of our systems, but it can also be equally rewarding. So our partners are Protofire, Avascan, HashQuark, and POA Network. So there are a number of important considerations when it comes to the bridge, but they ultimately boil down to the fact that the bridge and handler contracts bear the onus of relaying these messages across chains and must remain adequately funded in order for the bridge to remain operational. So if the bridge contracts were to run out of money, transfers would be stalled completely until someone refilled them. So the user pays for only a portion of the usage costs. While they pay for the deposit to the bridge contract on the initiating chain, they can't pay on the initiating chain for transaction fees that are needed to settle the transfer on the receiving network in the native asset of the receiving network. As mentioned, the bridge fee can only be paid in the native asset of the initiating chain. So while a bridge can and will have to be initiated with a set treasury of some amount of AVAX and some amount of Ether on either side, it also must have a mechanism for the bridge contracts to themselves collect funds, and also some mechanism for the operators to then trade native assets for one another and send them across the bridge to maintain a certain treasury balance on either side. This might be necessary in the instance of an imbalance. So an imbalance might occur if there are a lot more users sending transactions in one direction than the other. So if we take an example of, hypothetically, me and my friends are all interested in sending from Avalanche to Ethereum. And so we pay the bridge fee in AVAX to the contract on the C chain. Despite the fact that the bridge contract on Ethereum is the one that's going to have to procure Ether to spend on gas. So if no one is transferring in the opposite direction and no action is taken by the relayers, the Ether in the bridge contract will be depleted. So the operators would need to wrap AVAX, trade it for wrapped Ether, and send it across the bridge to bump the treasury of the Ethereum bridge contract. Establishing a proper incentivization scheme requires operators to set a fee that will cover the gas for transactions on the receiving network and the native asset of the initiating network. Plus, there will also be a margin so that operation of the bridge is profitable for relayers when including infrastructure and maintenance costs. This will be determined by the gas rates on both chains and the ratio between the asset prices. On some consistent time interval, the fee should be updated. That time interval should be dependent on the volatility of the two parameters, the gas rates and the ratio of price of the two assets. And so this periodic update of the fee will create the conditions for profitable operation of the bridge. So when we consider use cases, Pangolin is a Uniswap clone that is being deployed on Avalanche's C-chain. With the launch of the bridge, users will be able to transfer Ethereum assets onto Avalanche and trade them in a familiar fashion with lower latency and lower fees. Vice versa, people will also be able to send wrapped AVAX to Ethereum to trade on Uniswap, along with any other tokens that are native to Avalanche's X or C-chain. Immediately, it will also likely be useful to the bridge operators, as we mentioned previously, to trade wrapped AVAX and wrapped ETH on both chains in order to maintain sufficient funds in the smart contracts on either side of the bridge. In the future, we hope that many new and existing applications will try to experiment with Avalanche. As we're fully compatible with the EVM, once assets are introduced to our platform, any number of dApps can be deployed and leveraged, be it lending, oracles, dexes, or any of the other existing and undiscovered projects and tools that have been building on Ethereum. There is much to be imagined with the enabling of the transfer of generic call data that we have not even begun to think about or wrap our heads around. We welcome any and all experimentation on our platform, and we are really looking forward to collaborating with any interested members of the Ethereum community. Okay, so to close off the presentation, I'll show a beta demo of the ChainSafe bridge. Here we go. Okay, so the first thing that I'm going to do is go to my Gurley address on MetaMask to show you guys what my current wrapped AVAX balance is, and we see that it's 0. Okay, so now I'm going to connect my MetaMask wallet to the C chain, which is, I've already got it set up, but instructions to do this are available on docs.avax.network, along with instructions for deploying smart contracts with Remix or Truffle, if anyone wants to look into that. So we can see that I have some wrapped AVAX, but that my actual AVAX balance is running low. So what I'm going to do is I'm going to quickly head over to the AVAX test faucet, and I'll take my Fuji address, type in C dash, and then fill it in. Hit I'm not a robot, and then select all the images with parking meters. Alrighty. And request my AVAX. So just to show how fast this is, you can see it's 0, and we'll hit request, transfer complete. And there you go, it's immediately there. So the benefits of instant finality are really cool, and it's a great experience. So now I'm gonna go ahead and navigate over to the beta UI for the Chainbridge demo. And so I'm gonna also note that because this is a beta, we're using a relayer threshold of 1. This page probably just needs a refresh. Yeah, so there we go. We're connected to the AVAX chain. So this is a relayer threshold of 1, as I mentioned. So that means that we are only requiring one of our relayers to sign and vote on the proposal for the transaction to occur. So I'm going to go ahead and start the transfer and see. Here we go. MetaMask asks me to confirm. And so the gas rate on Avalanche is a static rate. It's currently set to 470 Gwei, and we have plans to drop it in the short term and implement a dynamic fee in the medium to long term. So I'm going to go ahead and confirm. And so now we see the transfer is initialized. It immediately goes into transit because the Avalanche transaction, as we saw, has almost no latency. So at this point now, we are waiting for the other parameters that are going to determine the overall latency on the bridge experience. So those are the speed and the availability of the relayers and the Ethereum network's block times, which, as we know, are 15 seconds, and then the associated confirmations that are required to finalize the actual transaction. So we will wait for this to conclude. All right, and so we see the transaction that was needed has been acquired, and so the proposal has passed. And now all we're waiting for is for enough Ethereum block confirmations to get through so that the transaction is finalized, and then it'll show up in my Gurley wallet. So yeah, just waiting for those confirmations. Okay, so after giving it a few minutes, we have confirmation. So now when I go ahead and load up my Gurley wallet again, I mean, first of all, we see that the mint clearly occurred, but when we load up the Gurley wallet, we see that I now have 0.5 wrapped AVAX. So yeah, thank you again for inviting me to speak at ETHCON. As I mentioned before, it was an honor. I really have been, deeply obsessed with Ethereum, as I'm sure many people here have for quite a while now. So I'm really happy to virtually attend and participate. If anyone is interested in using our Chainbridge deployment or in Avalanche as a whole, please feel free to reach out to me via the contact information shown in the next slide. Thanks again, and have a great one.